So going through trying to think about these mechanisms, when and how we use them. So let's start with a ketone. Oops. Let's start with a ketone. In step one, we're actually going to put it in acidic conditions. Right, we're going to be in acidic conditions. Right, so most of the time for most of these, what you should be thinking about is a couple of things. First thing, you should be thinking about what kind of charge is it. Is it basic or acidic? Right? If it's acidic, then you have to have overall plus charge all the time. Right? So if it's acidic, you have overall plus charge. If it's basic, overall negative charge. So that's the first thing I'd always think about is, am I in acidic, basic, or even sometimes neutral conditions? Right, so that's the first thing I'd always think about is acidic, basic, or neutral. Next thing I'd think about is like, right, what's my electrophile, what's my nucleophile? If I see H plus around, I'm guessing, right, I'm going to use it on this ketone, and the way I'm going to use it is to turn this ketone into something that, right now it's a good electrophile, right? The carbonyl is delta plus. So the first step is to protonate, right, which makes the carbon of the carbonyl even more delta plus, right? When we talked about acid catalyzed processes, right? So what we've done in the past here, if it was, say, an ester or carboxylic acid or an amide or something like that, we had addition elimination. But the difference here is, right, so step one, are we in base, B minus, acid, A plus, and neutral? What kind of conditions am I in? Two, what kind of carbonyl compound do I have? Right? What type of C double bond O? Right? Aldehydes and ketones are different, right? Remember, aldehydes and ketones, do they have leaving groups attached to them? Right? Aldehydes and ketones, right? A carbon and a hydrogen are not good leaving groups. So they react differently. That's the other thing I would notice. Do I have an aldehyde or a ketone? Right? So in this case we have a ketone, right? So I know it doesn't have a good leaving group. Right? So we talked about ways to put acetals on there, right? We use H plus and use acid and turn it into an acetal, that mask with sulfur or oxygen, right? We talk about the mask. But here there is no mask, right? I just have it in H plus, right? So in this case, right, I'm not using acid here to turn the carbon of the carbonyl into a better electrophile. I'm using it to turn it into a nucleophile. Right? So I'm going to do a tautomerization where, right, this H falls off, the electrons go there, and now what I have is the alpha carbon here, and I made H plus as well, right? Regenerate H plus as a catalyst. Right? I've made this into a electrophile or nucleophile. Nucleophile, right? I've made the alpha carbon nucleophilic. The other thing that usually is a dead giveaway, right? So let's say you have H plus catalyst first, right? So at this point, right, I can use, right, if you look at both of these things, right, this is the carbonyl as an electrophile. The carbon of the carbonyl is electrophilic. Here's this electrophile. And then I did a tautomerization and made an enol. Here it is as a nucleophile, right? So it could be both. At this point, the carbonyl could be an electrophile or a nucleophile. So it depends on what number 2 is going to be. So if number 2 itself is a nucleophile, what form would I use? I'd use this form as it being an electrophile. If number 2 is an electrophile, then I want to use the nucleophilic form, right? This enol form. So really it also matters what the thing you're reacting with is. So I put number 3. What are you reacting with? Right? If you're reacting with an electrophile, then the ketone part, or the aldehyde part, needs to be a nucleophile. Right? This is an enol form. Right? That's a nucleophile. So it really depends on what number 2 is as well. Right? What are you reacting with? So it's that same question we've been asking ourselves for a long time, right? What's the electrophile? What's a nucleophile? One thing is the electrophile. What does the other thing have to be for the reaction to take place? It has to be the nucleophile. So in this case, let's say I'll make number 2 this alkyl bromide. Well, what are alkyl bromides? They're always one thing. What are they? There's always electrophiles. right? They're always electrophiles. The carbon attached to the bromine is always delta plus.
So you always want the carbon to be the thing attacking?
Say it again?
You can never have like bromine attack?
Nope, bromine only wants one bond. You've never protonated bromine unless it's Br minus.
I know, so how would it get into Br minus? Like,
but it's not Br minus yet.
Okay.
Yep, so it's not Br minus. Right? So when it's still attached to carbon, that's an electrophile. Right? Think about it this way, bromine's super electronegative. Would bromine want to give up its lone pairs at all? Make another bond? Absolutely not. Right? So if number 2 is a electrophile, 2 is an electrophile, carbon 1 is delta plus, what form are we going to use? Are we going to use the protonated ketone form or the enol form? Use the enol form. Right? So these electrons come down. The alpha carbon attacks, always the carbon, never the oxygen. Bromine kicks up. So what new bond do we make between which two carbons? 1 and the alpha carbon, right? So it should, and in the same step I remade H+. So there's my alpha carbon, that's attached to 1, 2, 3. I also made Br minus to balance my charge. And then Br minus and H plus obviously would react. Then you get to this point right here. Using an enol to form a carbon-carbon bond. So what a process I would use. Are we in basic, acidic, or neutral conditions? That would tell you I'm making an enolate or an enol, or neither if it's in neutral. Right? What type of carbonyl compound do I have? Right? If I have an ester, things react differently with esters, right? Esters, those chapter 16 ones, esters, carboxylic acids, acid chlorides, anhydrides, amides, those all have leaving groups, right? Whereas ketones and aldehydes don't have good leaving groups, so they react differently. Right? Usually ketones and aldehydes are more often used, or can be turned into nucleophiles. Those other ones are harder to turn into nucleophiles. But ketones and aldehydes can both be electrophiles and nucleophiles. Here's a form of it with acid conditions. Okay, plus charges all around, right? Balance my charges, right? Plus, plus. Here is the carbon of the carbonyl being an electrophile. Here's the alpha carbon being a nucleophile. Depends on what form I use, right? Will dictate what else am I reacting with. What am I reacting with? If I react with an electrophile, I need a nucleophile. If this was a nucleophile itself, if this was an alcohol, then I'd want this form, right? If the thing I was reacting with was an alcohol, which is a nucleophile, I'd want this form. Okay? So let's take this another step and do the exact same thing we just did. We'll do this in acidic conditions, right? So we ask ourselves, we're in acidic conditions, so we show overall plus charge. Oxygen gets protonated. So here it is in its electrophilic form, or the carbon and carbonyl being delta plus. And before, we asked ourselves, well, we got to figure out what number 2 is, right? If number 2 is a nucleophile or electrophile, that would change what form we want this to be in. So what if I put this as number 2? This diol. The diol is number 2. Do I want to have this in the enol form or the protonated carbonyl form? What's the diol going to be? Is the diol a nucleophile or electrophile? It's a nucleophile. So that means I need this to be an electrophile. So I should leave it like it is, right? Good. So this is that way we put on, remember if we put on the mask, a way to protect a ketone or aldehyde. A little proton transfer, right? Tetrahedral intermediate. What's my best leaving group? It's the thing I just added. Right, so I want to do a proton transfer to get the hydrogen on this oxygen. Make sure we're always very careful about balancing our charges for these. Tetrahedral intermediate, water is a good leaving group. Right, we can't have this other oxygen attack because this is sp3 hybridized. It's going to be sterically bulky to get to. So instead we have these electrons come down from the other oxygen, take out the water. Now that turns that carbon to be sp2, which of course is planar. It's going to be much easier to attack. right? It attacks, forms a tetrahedral intermediate. Tetrahedral intermediate, we ask, is there any good leaving groups? Well, that's the last thing we just put on. So we're probably done. We can regenerate our catalyst. And we get our protected ketone in this case. But depending on, right, acidic conditions, basic conditions, what we're reacting it with, do we want the electrophilic form or do we want the nucleophilic form? Since alcohols are nucleophiles, we want this protonated ketone in the electrophilic form, not the enol. Right? Whereas before, we wanted it in the enol form because we were reacting it with another electrophile. So it really matters, right? Match and mix and match. Are you reacting with electrophile or nucleophile? What are you reacting it with? There'd be H plus here, right? So you got to know the going backwards too, right? So if you go backwards, this would get protonated. You get to here, electrons come down, kick this out. Water attacks, right? You just go through basically the opposite way, going this way. So you need to know how to deprotect as well. So it's confusing because the same conditions that protect it are often the same conditions that take it off, right? But if I use an excess of alcohol, I could get this on. Then if I use an excess of water, I could get it off. It's a way to think about it. So the reason why this is a protecting group is because now all of a sudden this carbon is no longer that electrophilic, right? So a Grignard or a hydride won't attack here, right? Or say if you wanted to react a ketone, like so let's say I have a molecule that's a ketone and an ester in it, and I want to do reactions on the ester. Well, I could put this on the ketone because it's more reactive than an ester. So now the ketone's protected or masked, and now you can do stuff on the ester, right? So this makes it less reactive, makes that carbon there less reactive. So that's why we do it.
That's what you kind of wanted us to do with the extra credit one?
That was one of the things in the extra credit one. The ideas was that was one way to do it. I saw lots of cool ways. People did cool ways to do it. But yeah, one of the ways is like we can use these things to mask it for a second and then take it off. It's one of those. In your class notes, I had a problem, at least one problem like that, where you had to react an ester in the presence of a ketone. You put the mask on, reacted the ester, took the mask off, you were done. Yeah, so maybe we can look at those again tomorrow too. Right. So let's take a reaction with two ketones. First up, we're going to take this ketone and react it with LDA. Right. So imagine this ketone's in the round bottom flask and react it with LDA. So what's that going to do? What's LDA? Lithium diisopropylamine, but even easier to think about. It's a large, bulky base. So in this case, with this ketone, I have two alpha CHs, right? Two types of alpha CHs. So which one am I going to pick if I react with LDA, with the alpha CH? The more substituted or less substituted? Less, because it's bulky, right? LDA is big. I'm going to go for the less substituted alkene, or less substituted enolate. So I'll take the H that's over here. So I'll call this the alpha carbon. 1, 2, 3, 4. So there's the H. LDA is the base. I'm going to make the enolate. Great. And I'm making the enolate on the less substituted carbon. This would be the kinetic enolate, we'd call it. Right? Kinetic. Right? Because it's the less substituted. All right, alpha carbon. Then what we're going to do, step 2, so we literally have our round bottom filled with this enolate floating around. We're going to start to slowly add another ketone, which I have drawn here.
Can I ask a question?
Yep. So remember, this is just one form of an enolate. I could draw these electrons going up and have the O minus, or I could just leave it as the electrons on the alpha carbon. Right? So I could have the resonance. So the resonance form of this is exactly this. These are exactly the same thing. They're just resonance structures of each other. Exactly the same. Yep. Okay, so I add in another ketone, right? So I have a full round bottom full of this enolate in either form. It doesn't matter which form it's in. A full round bottom of that. And I'm going to have it react with this ketone. I'm going to slowly add this ketone, dropwise. So let's number this ketone. 5, 6, 7, and then we'll call this whole thing 8. So which carbon am I going to attack? 6. So what two carbons are forming a new bond?
7.
Alpha and 6.
Wait. What are we attacking?
Where's the new bond going to be formed? What's my electrophile? What's my nucleophile? So my enolate is going to be my nucleophile, and this other ketone I'm adding in is going to be my electrophile. And so where is it electrophilic at? Carbon 6, right. So negative charge attacks. Pi bond breaks, electrons go up. So let's see. I always like to draw what didn't change. So none of this changed over here at all. The alpha carbon, oops, I'll label over there. The alpha carbon here is now bonded to carbon what? 6. So there's carbon 6, which is also bonded to 5. 6 and 5. It's also bonded to 7. And then 7 is bonded to the ring. 7 and then the ring. What am I missing? Oxygen's on which carbon?
6.
O minus on 6. Good. Alright. Alright, at this point, you're done. Right? You have tetrahedral intermediate. Do you have any good leaving groups on this tetrahedral intermediate? No? So a lot of times the next step will be, right, the third step will just be H+. Now, if you see H+ in heat, that makes it more likely to do an elimination. Or if you could make a pi bond that would be conjugated, that would also probably happen. So let's take a look here and see what happens. Let's see if we could generate a pi bond that would be very conjugated. So that first happens. We protonate that. And then we have, draw it all out again. OH. So let's see, 1, 2, 3, 4, alpha, 6, 5, 7, and 8. So do you think this is going to be worth it to do an elimination here? If I don't have a lot of heat and acid?
Yeah.
Where would the pi bond be at between? Where would the pi bond end up being if I did the elimination? Where is it acidic at still? Which carbon? It's still acidic. What's the most acidic CH bond in this molecule right now?
Alpha.
The alpha carbon, or carbon 2. But the alpha carbon is the one, right? Losing the hydrogen attached here would do the elimination. But the question is, if I put a pi bond between 6 and this alpha, would that be conjugated to the ring? No. Notice how that, right? There's that carbon 7. If that carbon 7 wasn't there, then absolutely I think we'd do the elimination, right? If that 7 wasn't there, then 8 would be right next to this pi bond, the ring would. There'd be a whole conjugated system, but just having this extra carbon 7 in here makes it less likely. Right? So those are old rules. We know those rules, right? If we can make a conjugated system, will we? But if we can't, there's not a great reason to make a pi bond, unless we force it. Unless I say heat. Right? If you see heat, that should be a clue, right, that I really forced it to do that elimination. So let's look at its number. Oh gosh, what number is that on the study guide?
4 on chapter 18.
4 on chapter 18. So we're looking at the study guide. And it's chapter 18, number 4. And that states, do you know how to use an enamine to form a carbon-carbon bond of the alpha carbon? And why it is more effective than an enol performing this reaction? Okay, good. So let's just first look at what's an enol and what's an enamine, right? So we already talked about how to make enols, right? Usually the enols are made with a little bit of acid and a ketone or an aldehyde. So this is an enol. And an enamine, hopefully, right? We've done that a couple times, how to make an enamine, right? How to put the nitrogen on, right? But remember, enamines are kind of cool because it takes a ketone or an aldehyde and a secondary amine, right? And turns it from an electrophile into a nucleophile. Remember, that's that Oompa Long chemistry. enamine. The same thing actually happens here, right? Where in both of these cases, the alpha carbon is the nucleophile, right? So the question is, do you know how to use an enamine to form a carbon-carbon bond at the alpha carbon? So do we know how to do it? Right, what would happen? What would happen if I took an enamine, and so this is going to be my nucleophile, so I need to react it with what? An electrophile. So what can an electrophile be? It could be another carbonyl group. It could be a carbon attached to bromine. It could be CO2. Let's just pick one. Let's say it's this little aldehyde. Formaldehyde. Right? So these electrons come down, just like they did with an enol or an enolate. Pi bond attacks, up it goes. We always want to make sure, balance our charges. Think about balancing our charges. So we formed a new pi bond. So the nitrogen now has 4 bonds, so it should have a plus charge. There should be an O minus. Does that look right? We made a carbon-carbon bond here, and we've balanced our charge. Yeah? So we ask ourselves the same question we always have. We have a tetrahedral intermediate, right? Do we have any good leaving groups? Nope, not now. 2 H's and a carbon, nope, no good leaving groups. So we're going to add in probably step 2 then. If this was step 1, step 2 is probably going to involve some H plus and water. Probably lots of water. So what's going to happen? We're going to protonate the O minus. Makes sense. And then we have water left over. What do you think water is going to do? Yeah, this enamine has now become, this is called something else, which I haven't told you what it's called because it sounds a lot like something else. So I don't think it's called an iminium.
Oh, like an amine? Like an imine. But it's an aminium.
Iminium, it's different. It's a nitrogen with a plus charge. Right? An imine doesn't have a plus charge. An imine, a nitrogen has 3 bonds. And an iminium, nitrogen has 4 bonds. That's why I haven't said it, because I can already see look in your eyes, you're like, oh my god, that is confusing. And it is. That's why I just didn't call it anything. Right? But it's, what can we agree with? What is this now? Is this a nucleophile or electrophile? Electrophile. Should water attack it? And from this point, we've done this mechanism. We've done this mechanism where we take the secondary amine off, right? So I'm not going to show those steps. If you need help with them, I can go through it with you. But it should be, you should end up with this. In a secondary amine. Those should be your 2 products. It'll take a couple more steps. It'll take some steps. Those are your final 2 products. Right? So when we form enamines, it's almost like it's like changing the chemistry, right? It makes, right, the alpha carbon nucleophilic. We can make carbon-carbon bonds. But then the nice thing is we can take the nitrogen off and get back to the ketone if we want the ketone. So that is the part where it says, do you know how to form a carbon-carbon bond? So this is showing you how to form a carbon-carbon bond. So you should have known how to make the enamine, make the carbon-carbon bond, and then how to take the enamine off. You should know how to do that. But then the other part of this question is, why is it more effective than an enol performing this reaction? Why is an enamine better at this reaction than an enol? Why do you think? So why would we even do enamines, right? We can make enols. Why take this extra step to put the nitrogen on? Why do you think? What is? Nitrogen's more willing to donate its lone pairs, right? Because remember, in this first step, what do we need to have happen? We need to have these nitrogen lone pairs come down for this to attack, right? And what's more willing to give up its lone pairs, nitrogen or oxygen? Nitrogen. So that's why we make the enamine, just because it increases the reactivity. It's a better nucleophile because it's nitrogen. Nitrogen is more willing to donate its lone pairs. So that's the second part of that. So let's let's go through some of our reducing reagents and like the fancy things we can do. So if I treated an ester with lithium aluminum hydride, if I treated the same ester with sodium borohydride, and then I treated that same ester with dibol H, what do I get?
Wait, can you add one more? Can you add the sodium borohydride? No. There's a sodium, wait, that's borohydride. We have it.
The sodium cyanoborohydride?
No, there's another one. There's another very tricky.
Is that the one with the D that any?
You can't think of any other one that you've shown us that's tricky?
Well, I could change out the hydrogens for deuteriums.
Not that. But you can show that too.
Okay, I'll do that. So this will all be step 1, step 1, step 1, step 1. Step 2 is always acid, H+. It's actually, yeah. You do the Feeser workup. All right. Esters, same starting material, different reagents every time. First, we got to remember what's more reactive, lithium aluminum hydride or sodium borohydride? Lithium. Why? Less orbital overlap, right? The aluminum hydrogen orbital overlap is less. That makes it a stronger source of H-, a more reactive source of H-. Are esters that reactive? Not really, right? So you're probably going to need something really strong here. So we're going to end up getting here. You added 2 H's here. Those H's came from the hydride. And then you're going to add an H on the alcohol that came from the H+. Right? So you keep track of where the H's came from. These 2 H's came from there. Actually, I take that back. That H also came from the H+. So the black H's came from reagent 1. The red H's came from the H+ in the workup step. We okay there?
H's, the red are from the H+.
Yep. These are the black H's. Let's draw them in. These are now black H's. Or black deuteriums. So keep track. But now we have sodium borohydride with an ester. Not reactive enough. That's the old classic, no reaction. Right? Not reactive enough. Also notice, as we look at both of these, the number 4 here, right? How many H- does each lithium aluminum hydride have? 4. How many H- does each sodium borohydride have? 4. If you go back and look at that reaction we do with the camphor reduction, you might have noticed, if you were looking at your equivalences, I don't know if we even use a 1-to-1. We might use a little bit less of sodium borohydride than we needed to even. Right? So to keep track of that. So it's worth 4, right? Because here we added 2 H's. Right? So we actually had excess H- here. Something else to think about. Okay, so far? So now we have this fancy one, dibol. Dibol is a bulky, right? Diisobutyl aluminum hydride. Diisobutyl, so 4 carbon chains would be a little bit bigger, right? So all of this, when we talked about aluminum H, boron H, that had to do with orbital overlap and electrons. Now if I start putting a bunch of junk around there, that's not about electronics, that's about sterics. So if I put a bunch of sterics on the aluminum, is that going to make it easier or harder for it to react? Harder. So it's not going to react as well. It won't react as well because there's a bunch of stuff kind of getting in the way. So in this case, we're going to stop, right? And we're actually only going to make an aldehyde plus an alcohol. So we're going to stop at the aldehyde here. We're only going to add 1 H. That's what's nice about dibol. It'll go from ester to aldehyde. So it'll stop there. I mean, there's a way you can get to an aldehyde, right? You just reduce, right? You could reduce and then do an oxidation like PCC or something, you get to the aldehyde, but that's 2 steps versus 1. Okay? Now we have lithium aluminum D 4. Deuterium deuteride. What are we going to get here? Exactly like number 1, except now we've added D's. And again, our H's in the workup come from that H+. How's that go? Good? All right, let's take a look at a alpha-beta unsaturated ketone. Well, I'll make an alpha-beta unsaturated aldehyde. Why not? And how is it going to react or interact with, I'll make it similar, this dicarbonyl. And I'm going to say in there, part 1, we're going to add in strong base. I'm just going to say, I'm going to say a methoxide. Right? That way it matches up with the ester. Right? So a strong base. So one of the questions here should be, oh no, now I have, right, I have this alpha-beta unsaturated, I think I have this dicarbonyl, and I have this strong base. So the hard part with these new ones, right, more than anything else is that instead of having just 2 things, right, and figuring out one's a nucleophile, one's an electrophile, here you usually have 3 or 4 things. So which of these things can you identify as either nucleophile or electrophile for sure? The ethoxide with the negative charge is what? Nucleophile. So I would say, right, I would automatically go, okay, this is going to be a nucleophile, right? That's a nucleophile. And it's a strong base, right?
It's a base.
Strong, yep, nucleophile, all bases are nucleophiles, remember? Right? Yeah. So it's just a particular type of nucleophile that takes H's. So this is a base. And so then we look at these two, we got to figure out which one is most likely to be the electrophile. So these bases, we've been doing all in this chapter, deprotonating CH bonds, right? And remember at the beginning I made you think about all the pKa's, right? Does this have any alpha CH's that are sp3 hybridized? No. Is this an alpha CH?
No.
Oh no. Oh no. No. Aldehydes, this H on aldehyde is not an alpha CH. Please do not deprotonate it. No. Don't do it. So we're kind of eliminating this. So where on this would it be electrophilic at? Where is it most electrophilic at?
In the middle.
The middle. What do you mean in particular? What in the middle? The CH bond, right? The CH bond. So we're going to deprotonate that. Maybe do some carbon numbering here. All right. Now this nucleophile is going to react with the aldehyde, which must be the electrophile at this point, right? The question is, where is it going to react at? Let's number these carbons. It's going to react at 5, 6, or 7. Which carbon is going to react at? 7. 7's the beta carbon, soft electrophile. This is a soft nucleophile, we call it, because it has resonance both ways. Right? So it attacks conjugate. We also call it that. So 3 is going to be bonded to which carbon? 7, and these electrons all go up. Now again, this is where it gets tricky. This is why I think numbering your carbons is really important. I like to draw the stuff that hasn't necessarily changed too much. So there's O minus, there's a pi bond, there. So I had 5, 6, 7. 7 was bonded to 3. So there's 3. 3 was also bonded to 2, which is bonded to 1, bonded to 4. Make sure these all numbers match up. 2, 1, 4. Missing anything? So far, so good? Okay. Now at this point, a lot of times they'll do is they'll say, well, you take this enolate and you could add in, right? Essentially, you could have it re-react with that and make this as a catalyst, or you'll say you add in H+. Right, that'd be step 2. So step 2 would be H+. A lot of times it'll be H+ water and heat. Now, when you see that, right, you know there's a lot of H+, there's a lot of acid, right? It's kind of implied. They'll never say it's excess, but it's implied. So I know it's not, yep, makes me mad too. But so how does an enolate react with H+? Where's an enolate nucleophilic at? Have we ever shown it to be a nucleophilic with oxygen? An enolate's always at which carbon? The alpha carbon. In this case, it'd be carbon 6, right? Enolates always react like this, where the alpha carbon is the nucleophile. So we put the H there. Put the H on carbon 6. So now let's draw out our product at this point. All right, we've added that H at carbon 6. So this is 5, 6, 7, 3, 2, 1, 4. So we're still in H+ in heat. We're not done yet. Now, if this had been a ketone, we'd be done. Or an aldehyde, we'd be done. But it's an ester. And esters, right, are different than aldehydes and ketones, right? Esters have good leaving groups. And in H+ in water and heat, esters can turn into what? Carboxylic acids. Right? So when you see esters and these dicarbonyls in this heat, you should H+ water and heat, you should think, oh, something else might happen here. So what else would happen? So we'll protonate the ester. I mean, I'm not going to go through all this because I think we hopefully know how to do this, right? At this point, we can turn ester right into what? It's going to turn into a carboxylic acid. Good. So I'm going to redraw this. I'm going to redraw it a little differently now. Good numbering system is important. 4, 7, 6, 6, and 5. Good. So we've turned ester at carbon 4 here, right? And we know those steps. At some point, you should know those steps, right? We'll make an alcohol as well. So, right, what else would be in there? We'd also have this alcohol in there as well. Right? Ester to carboxylic acid, we're there. So now, right, I think I've shown you this, I think I've shown you a decarboxylation, right, way to lose CO2, other ways, and here's another way, right? In these cases, as long as you get there, it's fine, right? But here's one way that you'll see this a lot. So if I move my arrows, right, it's carboxylic acid. So imagine here it's going to grab the pi bond attacks. The OH electrons go between that oxygen and 4. Right? And because that pi bond attacked this time, if I stopped right now, there'd be a plus charge on which carbon? 2. But I'm not going to stop. I'm going to break the carbon-carbon bond between 3 and 4 and have those electrons go between 2 and 3. So let's see if we can draw the product of that now. So hopefully now let's see what we have here. So I'm going to go up here. And we should have ended up with, there should be, where should there be a pi bond? What pi bond, where should there be a pi bond? Between 2 and 3, okay, good. So 1, 2, and 3. What else is 3 bonded to?
7.
Still bonded to 7, good. Which is still bonded to 6. Which is still bonded to 5. So none of that changed down there. That was just along for the ride. So 7, 6, 5. What else am I missing? What's 2 bonded to? An OH, very good. They got that O from over here, right? Where else am I missing? I'm missing this piece. Where did that go? What is that now? Now it's CO2, right? I'll even draw it so it looks goofy. There's that CO2, right? And now the question is, so we've done our decarboxylation. Right? And now, are we going to stay as the enol, or do you think we're going to tautomerize to the ketone? We probably tautomerize, right? So I would turn this back into a ketone. I mean, if you leave it at this point, that's fine. But you could always say, you know, this pi bond takes that, and these electrons come down and turn back into the ketone. But that's how we lost the CO2. It's nice, right? I mean, if you look at this, right, what size rings are good in organic chemistry?
4, no, 5.
5 or
6.
6, right? Look at this. This is beautiful, right? 1, 2, 3, 4, 5, 6. It's like a 6-membered ring transition state.
Wait, it's like.
Well,
Okay.
it is. It would be in like its transition state, and like on the top of the hill, right, where we drive the double dagger. It's a 6-membered ring, right? That's a perfect size to like get things to happen in organic chemistry.